Today we're going to be looking at the spectrophotometry lab related to the amount of blue dye in Gatorade. The first thing I did was created a stock blue dye solution. I wound up using 2 drops of blue food coloring in 250 milliliters in a 250 milliliter volumetric flask. You always want to make sure that your stock solution winds up with an absorbance between 0.8 and 1.2. If it's higher than 1.2, it's not really a valid measurement in your spectrophotometer. But if it's less than 0.8, then when students dilute it, it's going to get to a very, very low concentration that might not be valid either. So look for that range. The solution that I made, I wound up with an absorbance of 0.933. So it was right in the perfect range there. And then you're going to instruct students to make dilutions of that stock blue dye solution. All right, so let's review Beer's law really quick. Beer's law is A equals, I say EBC, where A is the absorbance, E is the molar absorptivity constant, B is the path length, and C is concentration. I always like to use this opportunity to talk about what does absorbance really mean. So here's my really simple drawing. In the spectrophotometer, there's a light source, okay? And then there's also a prism, and then there's a diffraction grating. And I didn't really show that very well. But the prism breaks up the light into different wavelengths, and then the diffraction grating helps to select for one particular wavelength. Okay. And in this lab, we're using a wavelength of 630 nanometers. And we chose that because it's complementary to the blue color of the dye solution. Because we want the light to be absorbed, all right? The reason why it looks blue is because it's reflecting back all of the blue light, and that's what our eyes pick up. So we want to use a complementary color. Then, so it's, the light is passing through, okay? What the spectrophotometer does is measures what percentage of light actually gets through the solution, okay? And we call that percent transmittance. Now, if you were to write that percent transmittance as a decimal, just transmittance, and then take the negative log of that, that's absorbance. So that relationship really helps us because it makes it a linear relationship with concentration. So again, a really simple drawing, but the more concentrated the solution, the more light will be absorbed and less light will be transmitted. Less concentration, you'll get more light transmitted and less light absorbed. So this is a good time to talk about this. Also, it's a good time to talk about the cuvettes themselves. So our cuvettes will typically be square, or at least rectangular, but the reason why is because then we can measure the specific length that the light has to travel through the cuvette. And that matters, because if you have, let me draw a similar thing like this. If I have the same concentration as this one, but it has to travel through more distance, more of that light is going to be absorbed. And so, how far it has to go really matters. And a good analogy for this one is like swimming pools versus the ocean. Typically, you can see the bottom of your swimming pool, but you're not, depending on where you are, you're not going to be able to see very far down into the ocean because it's a further distance. It's going to block more of the light, right? So path length here, B path length, that matters. But a lot of the times you're going to have a path length of 1 centimeter. So your cuvette is going to be 1 centimeter long to make your calculations easier. And really all of the ones that I've seen for high school use have been 1 centimeter cuvettes. They also tend to have these ridges on 2 of the sides. That's where the students should hold the cuvette. And then the clear sides, and you need to make sure that those go in the path of the light. You also should get them in the habit of cleaning those clear sides. You can use like a Kimtech wipe, or I just use paper towel or Kleenex, but just to get smudges off. And that's a frequent source of error that likes to pop up, where if there is a fingerprint or a smudge, that could block more light than should be, and you'd measure a higher concentration. Okay, so let's talk about that blue dye stock solution that we just made. So we wanted to make sure that the absorbance was between 0.8 and 1.2 for our stock solution. So we got a 0.933 as our absorbance for that stock solution. The molar absorptivity constant for this is 130,000. Now that's rough. It's provided in the lab manual that I use, but it is a rough value. It might be a little bit higher, it might be a little bit lower. However, it's not really going to matter because it's comparative. So, you know, if this concentration is a little too high or a little too low, it's okay. Because you're going to be making your calibration curve and then comparing it back to the calibration curve. It'll still be all right. So there's our molar absorptivity constant. Our path length is 1 centimeter, and you need to solve for concentration. And I like to do this ahead of time, and I just tell the students that I made a 7.18 times 10 to the negative 6 molar stock solution. And I just tell them that. I don't tell them what goes behind making the stock solution. And then from there, we can do our dilutions. So you're going to use the dilution equation, M1V1 equals M2V2, to calculate the concentration for each one of your dilutions that you're going to make. This also might be a good opportunity to introduce students to the proper way of making solutions. If you're strapped for time, they could use like volumetric flasks and like the proper dilution methods to create these different dilutions. You could even have one group do each concentration that you're going to use, and then in the next lab they can then test that using the spectrophotometer, making their calibration curve. So feel free to use lab prep as a lab skill that is a teachable moment, basically. So here I just gave one example. M1V1 equals M2V2. This is our stock solution. Now if I measure 8 milliliters of that stock and bring it up to a total volume of 10 with 2 milliliters of water, the new molarity when you solve will be 5.74 times 10 to the negative 6 molar. And you want to do that for all of your dilutions that you're going to make to form your calibration curve. Okay, so now that you have your dilutions created, we're going to place these one at a time into the spectrophotometer. Make sure that your spectrophotometer has been blanked with deionized water, and then set to 630 nanometers. And then if you want to, you can have students record the absorbance in the LabQuest itself or in your ProbeWare device. I like to usually have them do this by hand and record it just on paper so that we can graph it separately and create the calibration curve at the end. So here are the final results from this lab. We have the concentrations that we calculated using the dilution equation. And then each cuvette was placed in the spectrophotometer and we recorded the absorbance. Then what I have them do is I bring out the 2 different types of Gatorade. You can just do one if you want, or you can have even like a blue party and have kids bring in different blue drinks and test it that way. I know that these 2 types of Gatorade will fall within the values that are typically measurable, but you can always try it. So the 2 types that I use are Glacier Freeze and Cool Blue. And you put just some of them into a separate cuvette and record their absorbances as well. Okay, next thing you want to do is make our calibration curve, find the line of best fit. You can absolutely do this using the LabQuest or your ProbeWare itself. It has that capability. You could also use like a computer software, Excel, Google Sheets, something like that. I know that my students will have access to graphing calculators in class, whereas we don't always have access to the computers. So I like to make sure I do one lab where we graph it using the graphing calculator, and one of the other labs will graph it using the LabQuests themselves. So I have here just a TI-84 Plus and then a TI-84 Plus CE, because they look a little different when you plug these in. But both of them you'll go to Stat and then Edit, and you want to put your concentrations in one column and your absorbances in another column. Don't put the absorbances for the Gatorades, because those are our test solutions. Okay, then you want to make sure that your plots are turned on. So you go to Second and then Stat Plot, and you need to make sure that your one of your plots is on with your appropriate list for X and Y shown there. And then you're going to graph, and you see it looks the same. Both of these have the function where if it'll look kind of weird when you first graph it, but if you hit zoom and then go down to 9, zoom stat, or you just type 9, it will zoom right in, zoom 9, same thing. And you can see it gets a pretty straight line. And for the most part, these Beer's Law labs tend to have pretty good results. Then you need to find the line of best fit for that. And the method is roughly the same, but you would go to stat and then scroll over to calc and go down to linear regression. Now this is where it looks a little different, why I brought up the two calculators. The TI-84 plus CE prompts you for your X and your Y. This one does not prompt you. So for this one, I'm going to type in my X column and then comma, and then my Y column, and then hit enter. For the TI-84 plus CE, you just scroll down, calculate. And of course you get the same thing because it's the same line of best fit, but I wanted to show you both ways. Okay, so here is that line of best fit. I just plugged in the values for the slope and the y-intercept in here. And I want to show you how this relates to Beer's Law. Okay, since our X column was concentration and our Y column was absorbance, this number, our slope, is the same thing as the molar absorptivity constant times the path length. Well, our path length was 1 centimeter. So effectively, this number here is our molar absorptivity constant. And of course, that's a little bit off from the value provided by the lab manual that we looked at earlier, but that's okay, source of error. Also, you'll notice that there's a little bit of a y-intercept in the line of best fit. Even though we had the 0.00, it doesn't necessarily have no y-intercept, right, based on any errors associated with the experiment. So we talk about that too. So then this is the equation plugged in with absorbance and concentration. And then what we do is you take the two absorbances we found from the Gatorade. Glacier Freeze was 0.176 as absorbance, and Cool Blue was 0.571. Plug both of those in and solve for concentration. So you can see the concentration in molarity of the blue dye in those solutions. Always talk about some of the sources of error. If there was water left over in any of the cuvettes, that would cause the concentration to be lower than expected, which would decrease the measured absorbance. If there was a smudge on the cuvette or a fingerprint, that would block more light than expected and would make your concentration higher than it should have been. Those are really the two common ones. I think the only other thing I want to mention with spectrophotometry labs like this is that you can absolutely use a colorimeter instead of a spectrophotometer if that's what you have. They work pretty well. You just have a limited number of wavelengths that you can choose from. You can also use this, do this lab using a smartphone. There are some pretty good apps now that do color analysis. You just have to make sure that the students, do their cuvettes as normal. Cuvettes are fairly cheap. They're worth purchasing for this because then the path length for sure is 1 centimeter and the one side is very, very clear. Once they get their solutions in the cuvettes, they can just line them up on a white background. Make sure it's a bright white background and make sure that they have the blank as well right next to them. So that way when they essentially use their smartphone camera and the particular color analysis app, you can do a comparison between the blank and the different dilutions and graph it that way. And then you can take your two test solutions and compare that to the calibration curve to see where it fits. So definitely that technology is super useful. Another way that you can do this lab really is completely qualitatively. Students should be able to analyze graphs of this because they pop up on the AP exam, but if for some reason you're not able to do the quantitative portion, you can have them do the dilutions and line up and just visually see, okay, which one is closest visually for the for each Gatorade, and try to figure out the concentration that way.